Hi, this is Mike Michaelovich. I am co-founder of Complexica, and this is Unit 3 out of 6 unit video series for PRW that introduces subject of artificial intelligence. Today we would talk about prediction. This is unit number 3, and from previous segments you are familiar with this problem to decision pyramid, which was introduced during previous unit, and as I indicated today, prediction is the topic, and methods of artificial intelligence. Predictive modeling usually can be conceptually in a very simple way. You have some past historical data, for example, sales of particular product over the number of months, and the key question is what will happen next. And you can use variety of modeling tools. You can build linear, quadratic, exponential models. It doesn't matter what these expressions mean, and you can have different projections what would happen in the future. It may happen that the real life is different. None of these models is right for a variety of reasons. But if you look at this question, what would happen next, and you look at historical data, probably this is a little bit misleading picture, because usually you have additional data sets that you can use for making better prediction. Very often you have patterns from the last few years, not only for the last number of weeks or months, but number of different years of data which are available might be quite substantial. Then you can look at weather patterns, you can look at new products that were introduced that time and influence the sales results. It might be the information about past and current promotions is there. You can include in your forecasting model, or even competitors and their products. So altogether, taking all these data sets into account, it might be not that difficult to answer the question, what would happen next? Now, let me start with some basic observation. When you are facing prediction problem, then usually it is two-step approach. First, you build a model of this problem, and then this model would give you prediction for different circumstances. And needless to say, if the model is wrong, then prediction is also wrong. So when you build a predictive model for any problem, then the whole process is quite challenging because it is not really that straightforward. First of all, you should have all historical data available. And as I indicated earlier, it needn't be just data that relates to particular variable you try to predict, like number of units that would be sold particular week, but that can be extended by variety of external data. And then you should identify the key variables, and this granularity issue is a very important concept. I will talk about this in a second. Then you should have a methods to extract useful knowledge from data, trend, seasonality, dependencies between different variables like competitors, promotions, anything that matters. Then you should select appropriate model, whether it will be statistical method or neural network or some fuzzy system. Then after that, you should train, validate, and test the model to check whether you did everything right. And then on the top of everything, you should have a mechanism for regular updates. Sooner or later, every week, every month, every quarter, a new data would be coming in, and you have to have a method how to deal with these additional data. And again, if the model is wrong, then the answer would be wrong. Now, just addressing a single item from the list, granularity, it is quite important, and it is still more art than science. Let's say you are modeling some transportation network, you would like to estimate the travel time from one location to some destination, and then you look at the map of Australia, you have major distances given, but you can make it a little bit more granular. You can look at secondary roads, then You can go even deeper, looking at highways, secondary roads, and even some very minor roads as well, different connection. You consider everything, or you can go to the city level. You can look at streets and the plan of the whole city. You can go down. You can look at very small streets, and actually you can go forever. You can model traffic lights, you can model one-way streets, you can even model the frequency the lights change and the left and right turns and everything. Where to stop? If you model a map of Australia, it might be thousands of variables which can be taken into account. And of course, this would be unmanageable, not to mention updating the model, and there are many other considerations. So this aspect of granularity of the model is very, very important. Identifying key variables, staying with key variables, it is like walking very fine line. You don't sacrifice the precision of the model, but on the other hand, you don't overload with unnecessary information. There are many artificial intelligence-based predictive models. Some of you heard about neural networks, and we would talk about neural networks a little bit further in Unit 5. But basically, you are modeling human brain. You have set of neurons and connection between neurons. You have some inputs, and you expect some output. For example, input might be the week number and the product you are considering, and season and competitor behavior, or whether the product is on promotion this week or not. And then you are getting some output, expected volume, and might be something else if you are after more than one output. Then fuzzy logic, very powerful tool for predictive models. You build a set of rules and everything is defined in fuzzy terms. We don't say if speed is 60 kilometers an hour or the turn is 37 degree left and so on. Everything is described on conceptual level. If speed is high and turn is sharp, then reduce speed. And the same would be for sales, predicting sales. If the product is new and promotion is significant, then the volume would be high, for example. And then there is the whole science, how to reason with such intuitive rules and how to design the system to get at the end the crisp value that for this product this week you will sell 1725 items. Another possibility is random forest. So you have many decision trees. If this, then this, and you just follow particular branch. Most of you are familiar with decision trees, but the concept of random forest is very simple. You have collection of different decision trees, and they act like a committee. They vote for the best answer, and you take average or you count the number of votes and so on. And random forest as a collection of these decision trees would generate the best possible answer. Very powerful tool. Genetic programming, very promising, relatively new AI-based predictive models. You develop many computer programs to generate the answer. And then these computer programs are undergoing artificial evolution. You mutate them, you take two programs and you merge them together to generate a new program and so on. And you run this evolutionary process one generation after generation until emerging program would minimize prediction error, and you will get a model which basically emerge itself. Rather than building model, guessing rules and so on, you are just evolving a model. Very powerful tool. And from our experience, one of the best things you can do is to use so-called ensemble model, which is combination of many models which work together and they provide single output. This is what was done in the example I will be using a little bit later. Also, the simulation is a very powerful predictive model. Very often you are dealing with situations when there are too many moving parts, too many objects that interact with each other, and the only way to do it is to build some simulator, and you can visualize the results. So for example, you try to simulate the traffic. You have many variables you can play with in flow, on-ramp flow, maximum acceleration, even politeness of the drivers. And for example, you start this exercise. You look what is happening here, you increase inflow, so more and more cars are entering the highway, you increase on-ramp flow, more and more cars are coming from the side road. Even you can change the politeness of the driver, percentage of trucks entering the road, more and more trucks are there. You can block one line because it was accident, and you are just observing what is happening. So in a sense, you can say, this is a predictive model. I am doing a variety of things and I am observing that what would happen if this, what would happen if something else. Now let me move to our example. This is based on the project we done some years ago for General Motors. They are not only in business of producing new cars, but they are reselling their cars. They are coming off lease. And this is 1.2 million off-lease cars each year that they are sold at a variety of auction sites. So each day, their remarketing team in Detroit, they use business intelligence tools and reports to make a decision on a few thousand of cars. 1.2 million cars on annual basis would correspond to a few thousand every single working day. So every single working day, they were looking at making these up to 7,000 decisions. This car should be sent to this and that auction site, and another car should be sent to this and that auction site. And the problem is very, very difficult because cars are being collected at collection points, they are sold at auction sites, and as I said, the remarketing team is making these daily decisions for every single car return at any collection points. What would be the best auction site to send this car? And the problem is very difficult because you have to take into account several factors. Each car is unique: make, model, odometer reading, cruise control, sunroof, leather seats, variety of options, even damage level. Then you have to take into account seasonality. If you send convertible to Chicago in February, you would be regretting it for the next 3 months. Or you have to take into account very complex transportation network. The big trucks are capable of taking up to 10 cars from collection points to auction site. So if you move from 10 cars to 11 cars, suddenly you need 2 trucks, and you have significant jump in the cost function. And the timetable of transportation companies are very different. And you have to take into account petrol prices. If they go up, then probably prices of sport utility vehicles would go the other way. Suddenly yellow cars are more popular in California, and there is some premium you pay for them. So the problem is set in dynamic environment, and everything is changes on weekly or monthly basis. And on the top of that, one of the worst aspects of this problem was so-called volume effect. Let's say from your reports and business intelligence tools, you discover that the best price for white Pontiac is Jacksonville, Florida. You send 200 white Pontiacs to Florida, you depress the price, and everything is counterproductive, which means one thing: you can't solve this problem sequentially, looking at the first car, making decisions, second car, making decision. You have to look at the whole distribution, providing appropriate mix of cars. And on the top of that, since auctions are run every second week, you better remember what you did yesterday, 2 days ago, 3 days ago, because these cars you distributed a couple of days ago would be sold together with cars you are distributing today. This is why the problem was very, very difficult to solve. And predictive model, as I said, for this particular problem was a key. Let me repeat for the third time. If predictive model is wrong, there is really nothing to optimize. If you can't predict the price, sell price of a car at particular auction, then you are just walking in the dark, walking in the forest. So to make the right price prediction, you have to identify key variables, make model, year, odometer reading. You have to include additional variables and VIN number, which can be decoded into many other variables, color, features of the car, damage level. You have to take into account distribution of other cars for volume effect. You have to look at the date and auction site for seasonality factors. You have to know the current inventory information for this particular auction site. Seasonality I mentioned, and external data, petrol prices, current trends, and so on. You have to know everything. And then optimizer can talk to predictive models saying, hey, I suggest the following distribution of cars, and predictive model would look at this and he says average lift improvement per car is $213. You can improve on the current solution by that and much. So optimizer would say, so what about different distribution? Optimizer would make some intelligence modification to current distribution and ask predictive model what would happen with this one. And the predictive model say, in this case, you will get only 209 per car. So the optimizer would suggest another distribution, and predictive model would say, for this average lift per car is $219. And you repeat this process many, many times. So basically optimizer works with predictive model hand in hand, making some intelligent suggestions. What about this distribution, that distribution, and predictive model would provide with some accurate estimation of the merit of such distribution. And again, if predictive model is wrong, then the optimizer is searching in the dark. And as I said, there is no single predictive model that is best. In this case, we use ensemble models when with the question, what is the price of this particular car? Then you have your input variables when you look at this particular car and this particular distribution of cars, and date and auction site and current inventories and everything you need. And then you process this information through variety of models which work together. One model is paying attention to key variables like make, model, odometer reading. The other is taking care of special features, making some adjustments. And suddenly all these answers with different weights are combined together. And the system with some authority would say, okay, you would, for this particular car with this and that VIN number at this auction site, you will get $24,507. And let me jump to demo very, very briefly. This is the demo of the system. You can go to the distribution. This is the number of cars, few thousand cars to be distributed. And then you optimize you try to find the best distribution of cars. Let me stop the process here after a few seconds. Let's pretend it is optimal distribution. For each car, the system would give you auction location. For this particular Toyota Tacoma, which is sitting in Albany, New York, the best place to send it is Odessa Little Rock in Arkansas. But the point is that predictive model is responsible just for this column. If you do it, you will get $10,455. And the whole operations of the optimizer are based on these values. If these values are correct, the optimizer would do fantastic job. So let me return to the presentation, and let's summarize the results. The results were great. Average net lift was 250 per car, and you have to remember they are processing 1.2 million cars on annual scale, so suddenly we are talking about more than $250 million of unlocked value. And the team of remarketing people, 40 people, was reduced to 2 people who operate the system, and they were getting answers in seconds or minutes, not man days. And on the top of that, all decisions were very consistent, data-driven decisions, so no human intuition played any role in that. And on the top of that, and I will talk about this in Unit 5, the system had additional features. Predicted values were compared with actual values a little bit later when the car was sold. So we implemented this closed loop for making improvement, which was very, very important because they operate in a dynamic environment. This concludes our session on prediction. The next session is question answering live session, and the following unit would be Unit 4. We would talk about optimization. Thank you very much for your attention, and talk to you next time with Unit 4.